Hello everyone, my name is Shashank Watradka and I am a postdoc at Telecom Paris Tech. Due to visa issues, I was unable to travel to the US and I'm sorry for not being able to present this work in person. However, the organizers have kindly agreed to letting me send a video of my presentation, so I hope you enjoy it. This work is on local decoding and update of compressed data, and this was done jointly with Aslan Chamkirtan at Telecom Paris Tech. Locality in compression is inspired by problems of manipulating and storing large volumes of data such as biological datasets. Typically, such datasets are hosted on the cloud using services such as Google Cloud or Amazon Web Services. Storage is limited, and therefore one must use compression techniques in order to utilize storage efficiently. However, if we use traditional compression schemes such as lempel-ziv, then this would be inefficient, as recovering even a single file would require you to decompress your entire dataset. And moreover, frequently accessing and manipulating data on the cloud is expensive as it consumes energy. Therefore, it is extremely important to design schemes which utilize the least amount of storage on the cloud. Moreover, one must be able to retrieve short fragments of data by accessing a very small number of bits stored in the cloud. Also, we must be able to handle updates to short fragments of data by modifying a very small number of bits on the cloud. So our main goal is to design a compression scheme whose rate is close to the entropy of the source, and recovery of a single message bit can be done by probing a very small number of compressed bits. Updates to a single message bit can be handled by modifying a very small number of compressed bits. To ensure that the scheme is practical, we must have that the computational complexity of encoding and decoding is as small as possible. So let me first formally describe the problem. We are given an n-length message sequence, x1, x2 up to xn, taking values from a finite alphabet script x. The components are independent and identically distributed according to px. We are interested in fixed length compression schemes which have a very small, a vanishingly small probability of error, say order 1 over n. Now, such a compression scheme will output a binary code word of length nr, and our goal is to be able to recover individual symbols by probing a small number of code word bits. So the local decoder is going to be an algorithm which takes as input an index I between 1 and n, and based on the value of I, it probes a very small number of code word bits and outputs xi. The number of bits probed is going to be in general a function of the index and the message itself, xn, and we want to ensure that this is small on average. So the efficiency of our local decoder is measured by this parameter that we call the average local decodability QD. This is equal to the maximum over all possible I of the expected value of Q of I xn. So the averaging is done over the randomness in the source and possibly the algorithm itself. But for the purposes of this talk, we will assume that the encoder and decoder are deterministic and the only stochasticity comes from the message. Now similarly, we want to give an efficiency metric for updates, but even before that we need a reasonable model for symbol updates. The model that we'll use is the following. So we have a message x1 through xn and the corresponding code word here. Updates happen in the following manner. You first pick a location to update, say the ith location. You replace this. The update is basically done by replacing xi with an independent copy xi tilde. So xi tilde is distributed according to px and it is statistically independent of everything else. Note that xi tilde is allowed to depend on xi, but the marginal must still be equal to px. So This update model has a nice feature that the statistics of the old message and the new message are the same. So our goal is to design a compression scheme which can efficiently handle such updates. Now, in a practical scenario, the update algorithm will only know the location of the symbol to be updated and the values of the old symbol and the new symbol. It does not really have access to xn. So any algorithm that we design must be oblivious to xn. So what the update algorithm does is it takes as input I, xi and xi tilde, and based on these values it can probe a very small number of code word bits to get just enough information about xn. And based on the information that it has gathered by probing these bits, it modifies a very small number of bits to get the new code word. The goal is basically to minimize the number of bits probed and updated. So our measure of efficiency, which we term the update efficiency of the algorithm, is going to be the maximum or all possible I of the average number of bits probed and modified in order to replace xi with xi tilde. So our goal is to basically design a scheme which minimizes qd and qu simultaneously. Our contribution is the design of an explicit compression scheme which achieves rate close to the entropy. The local decodability and update efficiency are both constants independent of n but depend on epsilon. The overall encoding and decoding complexity grows only quasi-linearly in n. The rest of this talk will be structured as follows. I'll first describe a naive solution for local decoding and updates. I'll give a brief overview of what is known in the literature and a high-level description of our solution. Now, an obvious solution to the problem would be to take the n-length message and partition the message into blocks of b symbols each and separately compress each block. This can be done using some fixed length compression scheme such as typical set compression, but it does not necessarily have to be that. Now, if you want to ensure that the probability of error is vanishingly small, then b must grow at least logarithmically in n. Otherwise, we will not have concentration. So, and moreover, if we want to recover or update a single symbol, then all we need to do is look at the corresponding code word. So we can achieve local decodability and update efficiency of order log n. Now, one may wonder if isn't this good enough? After all, order log n is much smaller than n. However, note that if we want to ensure a small probability of error, then b, the size of each block, must be really large, and for the dependence between n and b to be b equal to order log n, n must be really large. So while this scheme is very simple and may look appealing, it is also very asymptotic. What is known in the literature about such problems? In the computer science community, problems of a similar nature have been studied under succinct data structures and bit probe models. So these are typically for worst case inputs. So the message is not random any longer, but comes from a set of allowable sequences. And in this case, it is not even known if one can achieve rates close to the empirical entropy of the source. In the information theory community, local decoding has been studied in prior work, but local updating has not been, and this is a novel contribution of our work. For local decoding, it is known that one can achieve rates close to the entropy, and local decodability, which is a constant independent of n. However, it is known that if we want linear encoders in order to simplify the design, then the local decodability must grow at least as fast as order log n. So any local decoder which achieves local decodability of less than log n must necessarily have a non-linear encoder. A major challenge in the in prior work is that they use constructions based on sparse bit vector compressors of this paper by Berman and others. These are in turn based on certain expander graphs, and it is not known how to obtain them explicitly. So in the literature, while it is known how to achieve constant local decodability, the algorithms there are not explicit, and it is not known how to encode them in polynomial time. So our main result is the design of an explicit compression scheme which achieves rate close to the entropy. The probability of error grows and decays super polynomially in n, but it's still sub-exponential. We achieve average local decodability and update efficiency of order 1 over epsilon square log 1 over epsilon. So this is independent of n. The overall encoding and decoding complexity is only quasi-linear in n, and our scheme is universal over memoryless sources. So the encoder and decoder, the local decoder, local encoder do not have to know the distribution px. To get some intuition about our compression scheme, let us revisit the naive scheme that we considered earlier. So you look at the n-length message sequence and you partition this into blocks of b symbols each. In order to ensure that the probability of error is vanishingly small, in order to have concentration, we must have b to grow at least logarithmically in n. If we choose b to be a very small constant independent of n, then a constant fraction of these blocks are going to be atypical with high probability. However, corresponding to every block, we can always associate a superblock, or corresponding to every block, we can look at the smallest superblock containing it, which is typical. So given any block, we can always find a subsequence of the message which contains this block but is also typical. So this superblock is what we will call the smallest typical neighborhood corresponding to this. For every block, we have different smallest typical neighborhoods. If the block is typical, then the smallest typical neighborhood is the block itself. If it is atypical, then the smallest typical neighborhood is going to be a larger subsequence. So the main idea behind our scheme is to encode information about the smallest typical neighborhood of every single block. But in order to achieve constant local decodability, update efficiency, and rates close to entropy, this encoding must be done in an intelligent fashion. So let me give a high-level description of our coding scheme. The coding scheme is done in multiple levels. At level 0, we partition the message into blocks of constant size each, and we separately compress each block using a typical set encoder. If the block, for example, this block, the blue blocks are typical and the red blocks are atypical. If the block is typical, then we store a non-zero code word which corresponds to the index in the typical set. If the block is atypical, then we store a zero code word to indicate that this is atypical. If the block is typical, then we modify the input by placing a marker to indicate that this portion is typical, and the higher level need not recompress it once again. So the output of the level 1 of level 0 encoder is going to be a sequence of code word symbols and also a message, a marked message for level 1. The encoder at level 1 looks at larger neighborhoods, so it basically groups together superblocks. So it groups together blocks to form superblocks and uses a similar approach of compressing each block separately. However, this in order to obtain efficient in order to ensure that the computational complexity is small, one needs to do this in a slightly more nuanced manner. So corresponding to each block, you generate a non-zero code word if that block is typical. If it is atypical, then you store a zero code word. If it is typical, then you place a marker to indicate that this part has already been encoded. And we keep proceeding in this manner to higher levels until we reach a stage where all the symbols have been marked and basically all symbols have been encoded. What is ultimately stored is a concatenation of all the level 0, level 1, level 2 code words. Now, how do we do local decoding with such a scheme? Suppose we want to decode a particular symbol. You first find the block it is contained in, and then you read the level 0 code word corresponding to that block. If the level 0 code word is if this code word is non-zero, then it means that this block is typical and you can read it directly. If the level 0 code word is 0, then it means that this block is atypical. So you look at a larger neighborhood, you probe the level 1 code word. If this is also 0, then it means that this neighborhood is also atypical. So you look at the level 2 code word. Now this is non-zero, which means that this neighborhood was typical, and using this you can reconstruct the sequence and you can work backwards to obtain the symbol that you're interested in. Now, a high-level explanation of why we can achieve constant average local decodability is that as you look at larger blocks, the probability that the block is typical keeps increasing exponentially, and therefore with overwhelming probability you will be able to recover a symbol by probing a very small number of levels. The idea behind designing the local updating algorithm is also very similar, and I'll omit that due to lack of time. However, you can find more details, the entire compression scheme and the proof in our paper, in our ISIT submission, which is available on my website. So to conclude, we studied simultaneous local decodability and update efficiency. We designed a scheme that achieves QD QU equal to constant in an average sense. An interesting open problem is to achieve QD QU equal to constant for the worst case inputs. With this, I'd like to conclude. Thank you for your attention.